Greetings of the day. Welcome to lecture number 39 on power quality problems and solutions. In last lecture, that's lecture number 38, we discussed the topology, the configuration, the structure, operating principle, and control algorithm of a shunt active power filter. In this lecture, we are first of all going to discuss series active power filter. Series active power filter. The problem with shunt active power filter is that it can very elegantly address all the load related or current related power quality problems, like it can mitigate or it can compensate the harmonics present in the load current. It can also compensate the reactive power demand of the load, making the line current or source current purely sinusoidal in nature and in phase with the voltage, thus giving unity power factor operation. But it's very difficult to use a shunt active power filter for mitigating the voltage related power quality problems. What are the various voltage related power quality problems? If I write here voltage related PQ problems, that's power quality problems, the various voltage related power quality problems are like voltage harmonics. This is one of the most predominant problems in voltage harmonics, voltage flickers, sag, swell, voltage unbalance, etc. These are some of the dominating voltage related power quality problems. Just brush up your memories. We have used one type of custom power device to address all these types of voltage related power quality problems. If you remember, that custom power device was DVR, dynamic voltage restorer. We have already studied DVR operation and we have seen how a DVR can address all these voltage related power quality problems. How it can compensate for voltage harmonics, how it can compensate for voltage sag, voltage swell, voltage flickers, voltage unbalance. Okay. Then what is a series active power filter? If all these problems are addressed by DVR, then what is a series active power filter? Series active power filter, again, I can say it is a subset of DVR. Okay. If I write here series active power filter, it is a subset of DVR, where DVR performs multiple objective functions or multiple functions simultaneously. Series active power filter is designed primarily to address some of the problems, like predominantly, I will write here, it predominantly acts as a filter. Predominantly acts as a filter. When I say it acts as a filter, so it compensates the voltage harmonics, that is the harmonics which are present in the voltage. It cancels the harmonics present in the voltage, making the voltage available across the load purely sinusoidal. This is the main function of DVR. Now, can a shunt active power filter do this voltage harmonic compensation? And can it provide protection against sag swells? Answer is yes to some extent, but it will be very hard for shunt active power filter to perform these functions. The size and rating of shunt active power filter to provide compensation against voltage sag, etc. will be very large. The size will be very large, rating will be very large, and cost will be very high. So therefore, for that purpose, for addressing these power quality problems, especially for filtration of voltage harmonics, we use series active power filter. Okay, and series active power filter, just like DVR, it has same structure. It is a voltage source converter or voltage source inverter, and it injects voltage in series with the load, and hence it takes care of voltage, some of the voltage related power quality problems. Okay, so Primarily, it suppresses the harmonics present in the voltage which is available at the point of common coupling or present in the source voltage, giving a clean sinusoidal voltage supply to the load. Okay, now that is the function of a series active power filter. Now let us discuss the classification of series active power filter. Just like shunt active power filter, a series active power filter it can be divided into three categories. Its classification is: number one, converter based classification. And when we say converter based classification, it's of two types: current source converter based series active power filter, series APF active power filter, and voltage source converter based series APF, that is series active power filter. This is one classification. Another classification is topology based. Topology based classification. And when I say topology based classification, on the basis of topology, we have single phase, half bridge series active power filter. This is one topology of voltage source converter, half bridge voltage source converter. And another is single phase full bridge series active power filter. And third classification is supply based classification. And on the basis of supply based classification, we have mainly two types of series active power filters: single phase series APF active power filter and three phase series APF. So this is the broad classification of series active power filters. Let us draw the schematic diagram or circuit diagrams of these classifications one by one. These different types of series active power filters one by one. So first of all, we have converter based classification. Converter based classification. When we say converter based classification, on the basis of converter, type of converter used, we may have current source converter based series active power filter, like current source converter CSC based series active power filter. And it will look like this. Let me show you. This is the source voltage. This is source or feeder impedance ZS. This is source current IS. And then we have DVR, this series active power filter connected here. Let me show you the diagram. Current source converter we have to draw. And this current source converter will look like this. Okay. We have DC bus, and on the DC bus we don't have capacitor. We have a huge large inductor, and this is the inductor current ID. Okay, right. Now this is the injection voltage, and this is the filter voltage, say for example plus minus VF, and then this is your non-linear load. This may be a single phase or three phase non-linear load, depending upon whether it is a single phase DVR or three phase single phase series active power filter or three phase series active power filter. Load current is IL. Okay, and load voltage is VL, and this load voltage will be purely sinusoidal. What does this DVR do? This is current source converter based DVR. It injects a voltage VF which comprises of harmonics present in the load voltage, in the source voltage. The source voltage may be distorted, maybe because of nonlinear load which is available here, or maybe because of nonlinear load which is available somewhere upstream. So this source voltage which is available across the load is distorted. And the DVR, what it does, it injects the harmonics, which are whatever harmonics are present in the source voltage. It injects the harmonics of equal amplitude and opposite size sign to those harmonics which are present in the source voltage. So the injected series active power filter injected harmonics will cancel the harmonics which are present in the source voltage, so that load voltage becomes sinusoidal. That means if this is your source voltage, say for example, roughly let us say source voltage is distorted something like this. It is not sinusoidal, and we want a sinusoidal voltage across the load. So what will your series active power filter do? It will inject the filter voltage. The filter voltage may be something like this, which we have discussed in yesterday's class, something like this. Okay. This comprises of harmonics present in the source voltage. So first of all, what you have to do, you have to estimate the harmonics which are present in source voltage, and then you have to design control algorithm in such a way that it injects the harmonics which are equal and opposite to the harmonics which are present in the source voltage. And when these harmonics are injected in series with the source voltage, these injected harmonics, or this compensation voltage, which basically comprises of harmonics, it will cancel all the harmonics present in the source voltage. Therefore, the voltage which is available at point of common coupling across the load, that is load voltage, will be purely sinusoidal. This is your load voltage VL. It will be purely sinusoidal. This is pi, for example, this is 2 pi, and so on. So load voltage becomes sinusoidal. This is load voltage. Although source voltage is distorted, but the series active power filter injects the compensation voltage or filter voltage, which comprises of all the harmonics present in the source voltage, and cancel the harmonics present in the source voltage, and make load voltage purely sinusoidal. Okay. Now, the topology that we have used in this case is current source converter. Current source converter has this type of topology. On its DC bus, we have inductor, not capacitor, and we don't have anti-parallel connected diodes across these IGBTs. Rather, we have series connected diodes like this. These diodes are connected in series with each and every switch to give reverse voltage blocking capability to IGBTs. I mean, if these diodes are not there, when this voltage is negative, your IGBTs may get damaged, because IGBTs do not have reverse voltage blocking capability. The reverse voltage will be blocked by diodes connected in series with each IGBT like this. So this is current source converter, or CSC based series active power filter. What about voltage source converter based series active power filter? Schematically, it will look like this. VSC, that is voltage source converter based series active power filter. It looks like this. This is source voltage, which is distorted. This is source impedance, ZS, source current IS, and this is the injected voltage, VF, by your series active power filter. And this is, say, load. It may be a linear or non-linear load. Linear oblique non-linear load. And load current is IL. Anyway, this is our voltage source converter based series active power filter. It looks like a DVR. Topology is same as that of a DVR. So this is VDC. This is it. This is voltage source converter. This is voltage source converter based series active power filter. Okay, so this is the converter based classification. What is the other type of classification? The other type of classification is topology based classification. Second is topology based classification. And on the basis of topology of the converter, voltage source converter that you are using, you again have two types of series active power filters. One is half bridge converter, half single phase, half bridge converter, half bridge voltage source converter based series active power filter. Let me show you the circuit diagram. We have a single phase circuit. This is source voltage, this is source or line impedance ZS, this is source current IS. Okay, fine. Then you have injection or interfacing transformer here. I will draw its diagram. This may be your linear or non-linear load. Let us say it is a non-linear load with load current IL and load voltage VL. The purpose is to make this load voltage sinusoidal in nature, whereas your source voltage is distorted. So you will use voltage source converter like this, but half bridge voltage source converter. Half bridge voltage source converter has, the other leg has two capacitors connected in series. Voltage across this capacitor is VDC by 2, voltage across this capacitor is VDC by 2. So the total DC bus voltage is VDC. Okay. Now this is our output of the converter. This is the injected voltage. This is the voltage injected by it. Okay. And you may have a filter, ripple filter also connected across this transformer primary or even transformer secondary. And this is the injected voltage VF. This is half bridge converter based voltage source converter. Okay. So this is the circuit diagram of half bridge, single phase half bridge VSC based series active power filter. What about full bridge? Second topology is single phase full bridge VSC based series active power filter. Series active power filter. And it looks like this. This is your single phase source voltage VS, which is distorted. This is line or source impedance ZS. This is source current IS, and this is DVR. This series active power filter injection transformer. It injects the compensation voltage VF, and this is your load. It may be a non-linear load, single phase non-linear load, or even linear load. Load current is IL and load voltage is VL, and we want this load voltage to be sinusoidal. So now we will use full bridge voltage source converter, not half bridge voltage source converter, as DVR. The DVR topology, DVR is basically voltage source converter, but what type of voltage source converter is used in this topology? Full bridge voltage source converter. In full bridge voltage source converter, both the arms or both the legs have IGBTs or switches. Okay, and this is your DC bus capacitor CDC with DC bus voltage VDC, and this is the injected voltage. Okay, so this is full bridge voltage source converter based series active power filter. Okay, so that is the classification of voltage, series active power filters on the basis of this topology. We have half bridge single phase half bridge VSC based series active power filter, and we have single phase full bridge VSC based series active power filter. And third type of classification is supply based classification. Supply based classification. And supply based classification, we have single phase, single phase supply based series active power filter. I am not going to draw single phase series active power filters. I have already drawn just few moments back. Single phase half bridge voltage source converter based series active power filter and single phase full bridge voltage source converter based series active power filter, they will come under this category, single phase series active power filter. Now I will show you a power circuit diagram of three phase three wire series active power filter. Three phase three wire series active power filter is used in those applications where your load is a three phase three wire load. Say for example, your load may be three phase adjustable speed drive, which does not use neutral connection. It's a three phase three wire non-linear load, of course. Okay, so the circuit diagram or schematic diagram is like this. This is phase voltage VSA, this is phase voltage VSB, and this is phase voltage VSC. This is the system neutral. This is line or source impedance ZS, and same in all the three lines, ZS, and this is the source current or line current ISA, source current ISB, and source current ISC. Now I have DVRs connected here. This is the interfacing transformer or injection transformer. This is for line A, this line for line B, this is the injection transformer, and for line C, this is the injection transformer. Now you will have three phase load. This is your three phase three wire load, maybe linear or non-linear or a combination of linear and non-linear loads. These are supply terminals ABC, and we want these load voltages VLA, VLB, and VLC. We want them to be sinusoidal because your source voltages are already distorted. For that purpose, we will use voltage source converter like this. Okay. This is DC bus capacitor, CDC with DC bus voltage as VDC, and this is three-phase voltage source converter for series active power filter, series APF, series active power filter. Now it injects the voltages like this. Similarly here, the injected voltage is this. Similarly here, third leg or third phase, third arm, it injects the voltage like this. Now the other ends have these are connected together. So this is injected voltage in phase A, VFA. This is injected voltage VFB. This is injected voltage VFC. Okay, and then you may have ripple capacitors also. I can show ripple capacitors across these injection transformer secondaries. Ripple filter, not ripple capacitor. This is RF CF ripple filter. Then this transformer also secondary also has ripple filter. You have ripple filter across all the three transformer secondaries. The purpose of these ripple filters, because your injected voltage is basically PWM voltage, it is pulsed like this. To remove the high frequency ripples around the switching frequency, you are connecting ripple filters, RF, CF, across injection transformer secondaries in all the three phases. Okay, it makes the injected voltage like VFA, VFB, and VFC without ripples, and those injected voltages will cancel the harmonics which are present in the source voltage, making load voltages sinusoidal. So this is about three-phase series active power filter. So that's all about series active power filters. We have learned that series active power filters basically, they take care of the harmonics which are present in the source voltage primarily, and they make the load voltages sinusoidal. These series active power filters can also take care of nonlinear loads. I mean, they can do current harmonic compensation also. But the best device for doing load current harmonic compensation is shunt active power filter, although series active power filter can also do the same job. So that is about shunt active power filter and series active power filter. Shunt active power filter basically acts as a filter against load current harmonics, and also it supplies load reactive power, making the source or line currents sinusoidal and in phase with their voltages, giving unity power factor operation. Series active power filter removes the harmonics which are present in the voltages at the point of common coupling, which are basically harmonics or distortions present in the source voltages, and it makes the load voltages purely sinusoidal. Okay. Now, sometimes what happens, the cost of when you use shunt active power filter or series active power filter, the cost is one of the main factors when you decide about the whether about the active power filters. In some cases, I will write here, in some cases, the cost of active power filter, whether it is shunt active power filter or series active power filter, is very high. I should not write cost, but the rating. The rating of active power filter is very high. It is as high as 80% of load rating. I mean, if your load is 10 kVA, the rating of your shunt active power filter may be 80% of load rating. That is 8 kVA. So therefore, the rating and hence size and cost of active power filter in certain situations becomes very high. And another problem with these active power filters is that they don't provide 100% compensation, perfect compensation. Like when you use shunt active power filter, it will provide compensation against load current harmonics only. It will not provide compensation against harmonics present in the source voltage. Similarly, if you use series active power filter, a series active power filter will provide compensation against source voltage harmonics, but it will not, perfectly take care of load current harmonics. So therefore, the compensation is not perfect by either of the two active power filters, whether it is shunt active power filter or series active power filter. In such situations, it becomes very difficult to go for these active power filters. I mean, the industries may be reluctant to use active power filters, primarily because of large rating, large size, high cost, and because they may not be providing perfect compensation against all types of power quality problems. So therefore, a lot of research was done to address these issues, and the researchers came up with a new breed of power filters, and that new breed of power filters was called hybrid power filters. Hybrid power filters, HPFs. Hybrid power filters are basically a combination of active power filter and passive power filter, or they are a combination of passive and passive power filter, or a combination of active and passive power filter. Okay, so when you have an active, say you have a shunt active power filter which will take care of current harmonics, you connect a passive filter also along with the shunt active power filter, which will provide rest of the, what you do, you have a shunt act. For example, you have to provide compensation against load current harmonics. You design your shunt active power filter, but you design your shunt active power filter in such a way that its rating is less. When its rating is less, it will not provide perfect compensation against load current harmonics. So it may partially compensate load current harmonics, and rest of the compensation will be done by the passive filter. You add one series or shunt passive filter that will take care of rest of the harmonics. So therefore, the work is divided between the two types of filters. Active power filter does some percentage of compensation, and passive power filter does the remaining this compensation, and therefore the compensation becomes perfect. And the advantage is that the rating and size and hence cost of active power filter is reduced, and the total cost of active power filter and passive power filter becomes less than active power filter alone. Okay. Similarly, if you have a situation where your load is facing voltage related as well as current related power quality problems, in that case, what you do for load related or current related power quality problems, you may use shunt active power filter, and for voltage related power quality problems, you may use series passive filter, or vice versa. You may use series active power filter for addressing voltage related power quality problems and shunt passive filter for addressing current related power quality problems. Or you may use shunt passive filter and series passive filter, or you may use shunt active power filter and shunt passive power filter. So both in combination. So that gives the concept of hybrid power filters. And when we say hybrid power filters, they are classified like this. They are classified as single phase hybrid power filters. I will write here single phase hybrid power filters, and they are three phase, three wire, three wire hybrid power filters, and three phase four wire hybrid power filters. Now they are further sub-classified into passive, active, and active, active. Passive dash passive hybrid power filter, passive dash active hybrid power filter, and active dash active hybrid power filter. This means your shunt power filter is also passive, series power filter is also passive. That's one classification. Another classification is your shunt power filter may be active, may be passive, and series power filter may be active. Or your series power filter may be passive and shunt power filter may be active. Or another classification is that both shunt as well as series power filters may be active power filters. Similarly, for three phase three wire, we may have passive passive combination, passive dash passive hybrid power filter, passive dash active hybrid power filter, and active dash active hybrid power filter. Active hybrid power filter. Same is the case with three phase four wire. Three phase four wire, I will write here passive hybrid power filter, passive active hybrid power filter, and active hybrid power filter. So this is the broad classification of hybrid power filters. Let me show you some of the configurations of these hybrid power filters. So some of the configurations are like this. I mean, you may have a situation, a hybrid power filter like this. This is source voltage. This is source or line impedance ZS, source current IS. You may have shunt series passive filter like this. This is series passive filter. I will write PF means passive filter, S means series. And you may have shunt passive filter also. Shunt passive filter is like this. passive filter SH means shunt, and this is your nonlinear load, and LL means nonlinear load. Load current is IL and load voltage is VL. So shunt passive power filter takes care of current related power quality problems like harmonics and reactive power, and series passive filter takes care of voltage related power quality problems like voltage harmonics. Okay, this is one combination. And another combination is, so this is passive passive. This is passive hybrid power filter. I mean, your series filter is passive, shunt filter is also passive. Another combination is same passive passive, but we can connect them the other way like this. We can first connect shunt passive filter. This is shunt passive filter SH shunt, and then we may connect series passive filter. Series passive filter, and this is our nonlinear load. This is another example of passive hybrid power filter. The difference being here shunt filter is connected nearer to load, across the load. Series filter is connected here. Here shunt filter is connected close to source and series filter close to load. But if you have to make a choice between the two, best choice is this: connect shunt filter directly across the load, because shunt filter takes care of load compensation. Okay, this is another type. Third configuration may be like this: source voltage, source impedance, source current. Okay, so then you may have series passive filter like this. PF1 passive filter series 1, and you may have shunt passive filter PF passive filter shunt SH, and you may have second series passive filter S2, two series passive filters and one shunt passive filter. This is your nonlinear load. This is also an example of passive hybrid power filter HPF. Another variation of this may be like this: source voltage, source impedance, source current. You may have two shunt and one series passive filters. This is PF-SH1, one shunt passive filter, and then you have a series passive filter, and you have another shunt passive filter, shunt 2. So two shunt and one series passive filter. So this is it. This is another example of passive HPF, hybrid power filter, right? Now let us go to passive active hybrid power filter. Now one example of passive active hybrid power filter will be like this. This is source voltage, source impedance, source current IS. You have a passive power filter, passive filter S for series, and you have active power filter. This is series active power filter S for series, and this may be your load, maybe non-linear load, or it may be even linear load. Now this is passive filter, this is active power filter, both are series. I mean, why we are doing this? Part of the voltage, I mean, they do the compensation for load voltage, so that the source voltage, harmonic compensation, so that your load voltage is purely sinusoidal. They do it because the part of harmonic compensation in the source voltage will be done by series active power filter, and part of harmonics compensation will be done by passive, series passive power filter. Okay, this is series, this is both will do voltage harmonic compensation, but they will do partial, so that the size, rating and cost of this series active power filter is reduced. So this is the example of passive active power filter, passive active hybrid power filter, HPF. Okay, another example is like this. You may have a shunt passive filter. This is passive filter SH for shunt, and series active power filter. This is active power filter series, and this is your non-linear load voltage is VL. Series active power filter will take care of voltage harmonics, and shunt active power filter will take care of current harmonics. So we have shunt passive power filter and series active power filter. So this is also an example of passive active hybrid power filter, passive active HPF, right? So another variation or another topology may be like this. Yes. Another topology may be like this. This is source voltage, source impedance. Okay, this is your, now you have shunt active power filter, shunt, and you may have passive series power filter. This is passive power filter, but it is series. Passive power filter series. And this is your non-linear load. Shunt filter is active power filter and series filter is passive power filter. This is another example of series. This is another example of passive active power filter. Passive active hybrid power filter. Passive active HPF. Another example may be, another type of topology may be like this. You may have a shunt active power filter, shunt, and you may have shunt passive power filter also. This is passive filter, this is also shunt, both are shunt. That means you are providing load compensation, load harmonics compensation, IL. Part of load harmonics will be taken care of by shunt active power filter, and part of load harmonics will be compensated by this shunt passive power filter. So that rating, size and cost of shunt active power filter is reduced. So this is another example of passive active hybrid power filter, HPF. Okay. Very quickly we will go now to next topology. Next topology may be like this. This is source voltage, this is source current, this is source impedance ZS. Okay, your series active filter may be passive. This is series, and this is passive filters, series passive filter, and shunt filter may be active, active power filter, shunt. So current harmonics will be taken care of by shunt active power filter, and voltage harmonics will be taken care of by series passive filter. This is also an example of passive active HPF, hybrid power filter, passive active HPF. And last topology that I'm going to share with you is like this. This is source impedance, source current. This is active power filter, series active power filter, and shunt passive power filter. shunt passive power filter. This is load, of course non-linear load. So current harmonics will be taken care of by shunt passive power filter, and voltage harmonics will be compensated by series active power filter. So this is also an example of passive active HPF. And last type will be like this: source impedance. This is series active power filter, and this is shunt active power filter. And this is your non-linear load. So this is active. Series filter is active, shunt filter is also active. This takes care of current harmonics, this takes care of voltage harmonics. So this is an example of active hybrid power filter, active HPF. Okay. Now let me give you a couple of diagrams, circuit diagrams of this three-phase hybrid power filters. A couple of circuit diagrams I will share with you. Or I can share with you. One diagram is this. VSA, VSB, VSC. This is source impedance ZS, ZS, ZS. This is C5, L5, C7, L7, and these are single tuned filters. And then you have high pass filter or damped filter. This is CH, RH, H for high frequency high pass filter, and LH. Similarly here, C5, L5, C7, L7, CH, RH, LH. This is C5, L5, C7, L7, CH, RH, LH. So these are series power filters. This is series passive power filter. And then your shunt filter may also be, passive like this. Similarly here also. And here also. Okay, this is shunt passive power filter. And then you have three-phase non-linear load like this. Say a three-phase diode bridge rectifier, which injects a lot of harmonics into the source current, which will be taken care of by this shunt passive power filter, and the source voltage is distorted, which will be taken care of by series passive power filter. So series power filter is passive, shunt power filter is also passive for three-phase, three-wire system. And then one last diagram I will share with you, or a couple of diagrams more like this. Next circuit diagram or schematic diagram is that our shunt series power filter may be active, and shunt power filter may be passive, maybe something like this. VSA, VSB, VSC, source impedance ZS, ZS, this is source current ISA or line current ISA, ISB and ISC. Then you have series active power filters like this. And this is your non-linear, three-phase non-linear load. Say a diode bridge rectifier, three-phase diode bridge rectifier. Again, I'm sharing this load, I'm drawing this load, diode bridge rectifier based load with a large filter capacitor at its output and some load resistance. This load is non-linear, so current harmonics has to be done. Let us assume current harmonic compensation is done by shunt active power filter, and voltage harmonic compensation is done by, so current harmonic compensation is done by shunt passive power filter, and voltage harmonic compensation is done by series active power filter. So this is your series active power filter. Let me draw the power circuit diagram of series active power filter. Voltage source converter based three-phase, three-wire series active power filter. This is DC bus capacitor voltage VDC, and this is the injected voltage. The other end is here. Similarly here, and similarly here. Okay, so injected voltage is here. Here injected voltage is VFA. Here injected voltage is VFB. Here injected voltage is VFC. And similarly here you have these are my passive shunt filters, star connected three-phase, three-wire star connected passive shunt filter. This injects current IFA. This passive filter injects current IFB, and this passive filter injects current IFC. So these injected currents will cancel all the harmonics present in the load, so that source currents are purely sinusoidal. Or in other words, the load current harmonics will be supplied by this passive filter, and source voltage harmonics will be cancelled by this shunt series active power filter. So this is your series active power filter, and this is shunt passive power filter. Shunt passive power filter takes care of load current harmonics, and series active power filter takes care of source voltage harmonics, making source currents sinusoidal in phase with their respective source voltages, and making load voltages also sinusoidal. And finally, I will share with you, this is also an example of passive active hybrid power filter. And finally, I will share with you the power circuit diagram of active power filter. So that will be like this. This is phase voltage VSA. This is phase voltage VSB. This is phase voltage VSC. This is source impedance ZS, ZS, ZS. These are source currents or phase currents, ISA, ISB, and ISC. Then you have a shunt active series active power filter. This is ripple filter, and injected voltages say VFA. This is VFB. VFC, and this is my three-phase voltage source inverter, which acts as a series active power filter. This is DC bus capacitor with DC bus voltage VDC, and this is, for example, injected voltage. Common point. These are the injected voltage. So this is series active power filter, series APF. Then you will have shunt active power filter, which will take care of current related power quality problems, and they will have a common DC bus. DC bus is common with DC bus voltage VDC. Shunt active power filter is just on right side of this series active power filter. And these are the injected currents. This is filter current or compensation current, IFA, IFB, and IFC. And this is three-phase diode bridge rectifier. Which is acting as a nonlinear load, a large filter capacitor at its DC bus, and this may be the load, and this is the connection. So load voltages are, say, VLA, VLB, and VLC, and load currents are ILA, ILB, and ILC. So this is shunt active power filter. Shunt active power filter will supply all the harmonics present in the load current, making source currents purely sinusoidal. And shunt active power filter will also do the reactive power compensation, making these source currents sinusoidal and in phase with their voltages, giving unity power filter operation. Series active power filter will cancel the harmonics present in the source voltage, so that the voltage applied across the load, these load voltages VLA, VLB, and VLC, are purely sinusoidal in nature. Okay, so you have already studied this configuration. If you remember, this is one of the custom power devices, UPQC, Unified Power Quality Conditioner. And there I told you UPQC is a combination of DStatCom and DVR. Although DStatCom and DVR have more wide range of applications, this is also a UPQC configuration, and of course you can say this is a subset of UPQC. This performs some of the functions which are performed by UPQC, like series active power filter, which is equivalent to DVR of UPQC. It performs mainly the source voltage harmonics compensation. And shunt active power filter, which is equivalent to DStatCom of UPQC, performs load current and load harmonics compensation. Okay, primarily. It may perform other tasks also, but primarily these act as filters. So this is the example of, or circuit diagram of, active-active hybrid power filter. Series power filter is also active, it is series active power filter. Shunt power filter is also active, it is shunt active power filter. So therefore, with these different combinations, we have different varieties of hybrid power filters, and these hybrid power filters provide almost full compensation, harmonics compensation in load voltage, load current, source voltage, and they also result in reduced cost of converters or shunt active power filters, reduce rating, reduce size, and reduce cost, and also reduce losses. So a lot of research is going on in this direction as hybrid power filters. And one of my MTech students few years back, he submitted his MTech dissertation on hybrid power filter, and in fact that work can be extended forward. More work can be done in that direction. So this completes our discussions on different types of active power filters. Shunt active power filter, which we have discussed in previous class, which takes care of load current harmonics, compensates load current harmonics, and provides load reactive power compensation. Then in today's lecture, we discussed series active power filter, which primarily addresses voltage current, source voltage harmonics. And also we discussed hybrid power filters, which is a combination of shunt and series power filters. Both may be passive, one of them may be active, or both may be active. So this is a wide variety of power filters, active and passive power filters, shunt active power filter, shunt passive power filter, and hybrid power filters, which address various types of voltage and current related power quality problems very elegantly. With this, I will end my today's lecture, and this marks the end of the filter part, power filter part of our discussion. We are now left with improved power quality AC to DC converters. Inshallah, in our next lecture, I will start discussions on improved power quality AC to DC converters. It may take us a couple of lectures, and with that, maybe 2 or 3 lectures. I will try to wind up within 2 lectures. That will mark the end of module 4, and of course that will mark the end of complete syllabus. So I advise all of you, and I request all of you to please go through this lecture and all previous lectures and give your feedback. All the best to all of you. Thank you.